Welcome to a mind-bending journey into the realm of large numbers. In this episode, we'll explore the fascinating world of numbers that push the boundaries of human comprehension. Large numbers can stretch the limits of our imagination. They emerge from the wonders of exponential growth, where quantities multiply at astonishing rates. Let's start our exploration with a number we encounter regularly, 1 million. It is represented by a 1 followed by 6 zeros. But what happens when we go beyond 1 million? We enter the realm of mega numbers, such as 1 billion, 1 followed by 9 zeros, 1 trillion, 1 followed by 12 zeros, and 1 quadrillion, 1 followed by 15 zeros. As we delve deeper into the world of large numbers, we encounter mind-boggling figures. For example, the estimated number of atoms in the observable universe is about 10 to the power of 80. It's a staggering number, but we're just scratching the surface. Numbers become even more colossal as we move up the scale. We have the googol, 1 followed by 100 zeros, the googolplex, 1 followed by a googol of zeros, and beyond. But there's more. We encounter theoretical numbers like tree-3, a mathematical construct that stretches the limits of our understanding. Tree-3 is an enormous number that dwarfs the scale of any quantity we encounter in our daily lives. Tree-3 is already an unimaginably large number, but in the realm of theoretical mathematics, there are indeed numbers that surpass its magnitude. One such example is the Busy Beaver function. First, let's understand what a Turing machine is. A Turing machine is an abstract mathematical model introduced by the British mathematician and computer scientist Alan Turing in the 1930s. It serves as a theoretical device that helps understand the fundamental concepts of computation and computability. At its core, a Turing machine consists of three main components: a tape, a head, and a control unit. The tape is divided into cells, each capable of holding a symbol. The head can read and write symbols on the tape, while the control unit determines the machine's behavior based on its current state, and the symbol under the head. The Turing machine operates through a sequence of discrete steps. During each step, the machine performs the following actions: it reads the symbol on the tape under the head, consults its internal state, decides the next action based on a set of predefined rules, known as transition rules, writes a new symbol on the tape, moves the head left or right, and transitions to a new state. Through its ability to manipulate symbols on an infinitely long tape and follow predetermined rules, a Turing machine can simulate any computation that can be algorithmically described. It can solve problems that can be solved by an algorithm, given enough time and resources. Turing machines are significant because they laid the foundation for the theory of computation and the development of modern computers. They helped establish the concept of an algorithm, computability, and the limits of what can be computed by machines. Turing machines serve as a theoretical framework for studying the fundamental properties and capabilities of computers and computation. The Busy Beaver function is a mathematical concept that represents the maximum number of steps a Turing machine with a specific number of states can perform before halting. The value of the Busy Beaver function grows rapidly as the number of states increases. In fact, it grows faster than any computable function. While the exact values of the Busy Beaver function are not known for larger numbers of states due to the problem's undecidability, it is believed that they quickly surpass the scale of tree 3 and any previously mentioned large numbers. The growth of the Busy Beaver function demonstrates the immense complexity and unbounded nature of mathematical exploration. These numbers are more than just abstract concepts. They help us appreciate the vastness and infinite possibilities of mathematics. They challenge our perception of the world and invite us to explore the wonders of exponential growth and the mysteries of the universe. And think of this? Despite the mind-boggling scale of numbers like tree 3 and the Busy Beaver function, they are still considered infinitely smaller than infinity. Infinity, as a concept in mathematics, represents boundlessness, an endlessness that cannot be quantified or contained within a finite value. No matter how large a number we can imagine or conceptualize, it remains finite in comparison to infinity. This discussion on large numbers and infinity can lead us to potential paradoxes and intriguing philosophical questions. One such paradox is known as Hilbert's paradox of the Grand Hotel, proposed by the mathematician David Hilbert. In this paradox, we imagine a hotel with infinitely many rooms, each occupied by a guest. Now, suppose a new guest arrives, seeking a room. Despite the hotel being fully occupied, the manager can accommodate the new guest by shifting the current occupants to the next room number. In this way, every guest moves to the room with a number 1 higher than their current room. As a result, room number 1 becomes available for the new guest. This paradox challenges our intuition about infinity. It demonstrates that even when all the rooms were previously occupied, by cleverly rearranging the infinite set of guests, we can always make room for another guest. Paradoxes arising from the concept of infinity highlight its counterintuitive nature and expose the limitations of our everyday comprehension. These paradoxes exist in theoretical mathematics, and are not encountered in the physical world. They serve as intellectual exercises that expand our understanding and inspire further exploration. Here are some captivating questions that may arise. Can we conceive of numbers that surpass the magnitude of tree 3, and the Busy Beaver function? Are there theoretical constructs that transcend even these mind-boggling quantities? How can we refine and expand our understanding of infinity? Are there alternative mathematical frameworks or notations that could help us better grasp its intricacies? Can we resolve the paradoxes that arise from infinity? Are there new insights or mathematical tools that can reconcile the infinite with our finite understanding of the world? What practical applications might emerge from studying large numbers and infinity? How can these theoretical concepts be harnessed to advance fields like cryptography, optimization, or quantum computing? Are there deeper connections between large numbers, infinity, and other branches of mathematics, such as set theory, analysis, or topology? How can exploring these connections enhance our understanding of fundamental mathematical principles? As we conclude our exploration of large numbers and infinity, let us celebrate the endless possibilities of mathematics and the unending quest for understanding. May future mathematicians embark on their journeys, armed with curiosity and determination, and unravel the secrets that await in the realm of numbers. Video sponsored by Pictory.a. Use promo code IMIN75 when you sign up and support the creation of more productions like this.